We're going to talk about the law of sines. This whole unit, chapter 8, the three things that we're doing have to do with trigonometry. And this is kind of after the right triangle trigonometry with sine, cosine, tangent. There's probably the second most important thing, which is the law of sines. And so to kind of demonstrate how this law of sines came about in 8.6, they have this kind of example, think about it thing. And we have two rangers in towers that are 10 miles apart. And they're in a national forest, and they spot a fire that's far away from both. So the fire is probably somewhere over here. And one ranger recognizes the fire location, knows that it's about 4.9 miles from the tower. That's Ranger B. And then with that information and the angles that are given, we want to figure out the distance of the fire from the other tower using only right triangle trigonometry. Now the secret to this is to draw a perpendicular from that fire and use some right triangle trigonometry. As I look at the triangle that's on the right-hand side, this triangle right here, if I wanted to find out the distance of this perpendicular segment, which I'm going to call H, then I realize that in the blue right triangle, I see that I have an angle. I'm looking for the side that's opposite to that angle, and they give me the hypotenuse. And yesterday with SOHCAHTOA, we learned that when we have an angle, opposite, and hypotenuse, we use sine. So I know that the sine of that 53-degree angle will be equal to the opposite side, which is H, over the hypotenuse, which is 4.9. And then we also learned that we can go into our calculator, make sure we're in degree mode, and we can type in the sine of 53 degrees. And we have to go to 4 decimals whenever we use trigonometry. So that means I'm going to use 0.7986. So 0.7986 equals that H over 4.9. And yesterday we also talked about if our variable is on top, what do we do with the two numbers? We multiply. So we're going to take that 0.7986 and times it by 4.9. And we find out that that height to the nearest 2 decimal places, because it's not trigonometry anymore, it's a variable that we're solving for, is 3.91. And this, since we're talking about miles, would be in miles. So I now know that that height is that many miles. Now if I wanted to, what I could do then is I could find out how far this distance is, and we can call this distance maybe x, because now we have a different triangle. We have the left-hand triangle right here in green. And in that triangle, I can set up a similar ratio as I did before, but now I have a different angle. The side that's opposite, that I now know, which is 3.91 miles. And I'm looking for the hypotenuse. So that means I've still got the sine of this time the 29-degree angle, and it's equal to the side opposite, which is 3.91 that we just found, over the x that we're looking for, which is the hypotenuse of the green triangle. If I find the sine of 29 degrees, I find out to 4 decimal places it's 0.4848. And that's 3.91 over x. This time my variable is on the bottom. So in order to solve that, I'm going to take the 3.91 and divide by the decimal. and I get to the nearest 2 decimal places, 8.07. And again, that's in miles. And what this shows us in the end is that the ratios of the sines to their angles are equivalent because they match up with the height. The way that we're going to write that in our law of sines looks like the following. I know that the sine of any angle in a triangle, let's just say we use the letter A, over the side that's opposite to it, which we always call the lowercase of that same letter, should be equal to any other sine in the triangle, maybe a B, compared to its side opposite. Or even the third side in angle, the sine of C, over its side that's opposite. This is called the law of sines. Now the cool thing is, in the law of sines, in addition to every ratio of a sine of an angle divided by its side that's opposite, you could also flip those ratios and also have the same kind of relationship. Meaning I could have done side A over the sine of angle A equals side B over the sine of angle B, so on and so forth. For some reason I always write the sine thing on the top and the side on the bottom, but you could flip them all and you would have the exact same relationship. Either way is okay. The only time that you really should be using the law of sines is when you have, you're given, I guess I should say, 2 angles and 1 side. If you're not given 2 angles and 1 side, then you should not be using the law of sines. 2 angles and 1 side. So in this first example here, I'm just going to show you how to find the different pieces in this triangle. First of all, we know that in any triangle, all of the angles add up to 1/8. So if I wanted to, I could find this last angle here quite easily by taking 180 and subtracting off the 135 and subtracting off the 14. 31? Okay, thank you. So 31 degrees is this angle measurement just by doing some simple math and knowing that there's 180 degrees in the triangle. So if they ever asked you for angle C or whatever angle they call that, that's the way you would do it. Notice that in this particular problem, there are 2 angles that they give us and 1 side. So let's say, just for fun here, that I know that I'm looking for the side over here, which is the very longest side across from the 135 degree angle. I'm going to call that little letter A because it's across from capital A. And what I know is that if I want to find that little a, I know the sine of 135 over little a should be the same relationship as the sine of that 31 degree angle over the side that was across from it, which was 10. Because this is the law of sines. The sine of an angle divided by the side across from it is equal to the sine of an angle divided by the side across from it. And the only one that we know for a fact, completely ratio-wise, is the 31 degree angle and the 10 side that are across from each other that are completely filled out. Now this is when we do that famous, you might recall, cross-multiply thing. I multiply these two things, and I multiply these two things, and then I solve. I talk about it a little bit differently. What I look at is I notice that in this particular proportion, the a is the only thing that's unknown. So what I'm going to do is I'm going to multiply the things that are across from each other that I can figure out, meaning these two things, the 10 and the sine 135, and divide by whatever's left over. Or in other words, if I'm looking for my a will be equal to 10 times the sine of 135 degrees divided by the sine of 31 degrees. And I can type that all right into my calculator and I will pop my answer for the letter A. So 10 times the sine of 135 divided by, sorry?
11.14?
I don't know, I'm going to try it. Let's see. 10 times the sine of 135, don't forget the ending parentheses, I get 13.73. Don't forget to end your parentheses. So 13.73 is the length of A. Now, to find the other side, which is the only one that's left over, which is side B, over here, I would do the same kind of thing. I would go, oh, hey, the sine of 14 degrees divided by side B is equal to, and then I would use my red ratio again, the sine of 31 over 10. And in order to figure this one out, it looks very similar. I'm going to multiply the two things that I know that are across from each other, the 10 and the sine of 14, and divide by whatever's left over. Or in other words, I'm going to go B, whoopsie, sorry, is equal to 10 times the sine of 14 degrees divided by the sine of 31. So in my calculator, I have 10 times the sine of 14. What? Divided by the sine of 31. .7, because the 7 makes the 9 go to 0, makes it go to whatever. So 4.7. So I get 4.7. And these are both, of course, in miles. So in case you didn't label the first time, make sure you label. These are in miles. Okay, so in our first example here, after our investigation one, again, we're going to probably have to find all the different pieces. So the first thing that I'm going to do is I'm going to find the missing angle, because to me that seems like the natural thing to do. So I have 180 minus my 81 minus my 73 for a grand total of 26. Thank you. 26 degrees. So this angle over here is 26 degrees. Now I have two sides that I can find. Doesn't really matter what we call them. Let's say we call that first side x. If I call the first side x, what I know is that the sine of that 26 degree angle that we just found over the side that's across from it, 25 kilometers, should be the same as the sine of 73 degrees over that x, because the 73 degrees and the x are across from each other. I look at the two numbers in my proportion that I can work with. So I take 25 times the sine of 73 and divide by the sine of 26. So 25 sine of 73 and it was divided by the sine of what? 26. Thank you. Don't forget your parentheses. I get 54.54. It's weird how we're getting a lot of the same numbers right in a row. 54, 54. So I get x